So, one thing I forgot to address was the unit on relativity. Just to make sure that you guys have the right information, Lee and I were going to go through the documents that you guys created, and we'll turn them into PDFs. And once they've been turned into PDFs, it means that we've looked at and validated the content on those documents, and you can use them, whether they're questions and answers or whatever. Okay? All right, so let's go back and start this topic. We left off on a table. Let's complete that table as like a intro, as a summary of what we did last class, and then we'll get started. So we left off your answers. What did you guys get for what happens in alpha decay? What happens to the atomic number? -2. What happens to the mass number? How about for beta minus decay? Minus +1. And mass number? Change. For beta decay or beta plus decay? This one is -1. Mass number unchanged. And in gamma, yeah, no change here, no change here. Another, I'm just going to go back real quick and talk about some of these reactions here. I posted this reaction. It's not going to help. It's crappy because I think our projector is not very good. But anyways, what matters in these nuclear reactions is that everything balances out. Okay, so we're going to talk about nuclear reactions a little bit at the end, but ultimately you don't even need to understand what's going on as long as you have the same number of protons on both sides. Sorry, same number of nucleons on both sides, the same charge on both sides. Obviously, like a chemical reaction, if there's any coefficient in front of it, you have to keep that constant as well. But ultimately, it just has to do with keeping everything constant. The idea of conservation of mass is still in effect here. And so you have to follow those rules. We'll do a couple examples later on. It's not too difficult. All right. So that leads us to this topic here of radioactive decay. And does anyone recognize this symbol, by the way? Upside down what? Gamma? It's a lambda, which represents half-life. It's also a symbol of a video game, very popular video game. That's what I was hoping for. No one? No. Okay, no, it's just me. It's fine. But yeah, so we're going to be talking about half-life and things like that. You've heard of half-life before, right? Yeah, a little bit. If you haven't, it's okay. Well, basically do it as if you'd never seen it before. So basically a half-life is the amount of time for any substance to decay to half of its starting mass. So if whatever mass I have, if I have 10 grams of it, and it takes 5 days to get for it to decay spontaneously to 5 grams, then what was its half-life? 5 days, exactly. It took 5 days for half of it to go away. What that half became, it doesn't really matter. What matters is that it's no longer what it started off being at. So if it started off as carbon-14 and became nitrogen-14, we don't care about the half-life of nitrogen-14 because what we're looking at is the decay of carbon-14, or not what it became. And this happens because all atoms are pretty unstable. And I say pretty unstable because everything has a half-life, except some things have a half-life that's so long that we can't even measure it. It's never. Carbon-12, for example, has an undefined half-life. The half-life is like you look it up, it says undefined because it's so long. But it doesn't mean that it doesn't have a half-life. It just means that it's so long that we can't measure it. We use this for many things. Nuclear reactions is one of them. Carbon dating is something that we're going to be talking about today that requires us to understand what half-life is. The symbol for a half-life is lambda, right? That's like the 8th time we see lambda in this course. That means 8 different things. So just make sure when you're studying for your exam, you know in what situations or what when you're looking at the equations, you know what the symbols mean. Because I'm just going to give you a bunch of equations. Doesn't you guys need to know how to use it? So if you can't understand if it's wavelength or half-life, then that's going to be a problem for you when you're studying. And then you would write it something like this. So the half-life of C12, or the 12th isotope of carbon. By the way, what does the 12 represent in my C12? The number of nucleons, exactly, right. So if I'm looking at C12, which has, it's C, so it's got 6 protons, and it's got 12 nucleons, and that means it's got 6 neutrons. That's relatively stable, and there is no defined half-life, and we would typically say it's non-radioactive, which is not necessarily true. If it's radioactive, there's very, very, very little radioactivity happening. Everything is slightly radioactive. And then you get to the more unstable carbon isotopes, for example, C14. Now you have 2 extra neutrons, and it's a little bit less stable, and the half-life is still pretty long. It's 5,730 years approximately. And that means that for every 5,730 years, half of your carbon-14 will decay into something. Right? And now I can specify to you that it's a beta decay, and you can determine what it decays into. I can tell you that it's a alpha decay, and you should be able to know what that means as well. But the point is that after 5,730 years, it started off as C14, half of it became something else. And then you get to the more unstable isotopes like C16, which has a half-life of less than 1 second, right? So you can't even hold on to this atom for that long. And a lot of these new elements that you guys see being discovered, like the new elements you're going to add to the periodic table, yes, they exist because they just smash a bunch of protons together and neutrons together, but their half-life is so short that, for all intents and purposes, they're not real, right? They're just, yes, you can make an infinity number of different elements by just putting an infinity number of different combinations of protons and neutrons. But at a certain point, their half-life is so short that they can't even exist long enough for us to be able to consider them in existence. All right, so super easy question here. If you start off with 10 grams of phosphorus 32 rather, what mass of P32 will be left after 1, 2, 3, and 4 half-life? So what do you think how much is going to be left after 1 half-life? 50%? What's 50% of 10 grams? 5 grams. Right, so 1 half-life, so I'm going to say 1 lambda. It's going to give us 5 grams. Oops. What about 2 half-lives? 3.5, 3 lambda. 1.75? 1.20. And 4 lambdas? 0 point. 0.6125, roughly speaking. And really the pattern here is I'm just dividing it by 2 each time. Dividing by 2, dividing by 2, dividing by 2, right? And we don't always measure things in how many multiples of half-lives. I'm just doing this to simplify it for the first example. We would sometimes say that something has exhibited 1.5 half-lives, and then you have to actually do a calculation. You won't be able to do it in your head like that. But it's a very straightforward calculation. What's important to remember is that there's a starting amount, and then we can use in time, and knowing its half-life, we can figure out exactly how much we have left. So let's do some of those equation works. This is what the half-life equation looks like. N represents the amount of stuff you have, whether it's at time t or initial amount. And this amount can be defined in any units, as long as the units are constant, right? It can be in grams, it could be in atoms, It could be in moles. It doesn't matter because the conversion factor for all of those is the same for all atoms. And since you're going from the same atom to the same atom, right, you have the initial amount of the carbon-12, let's say, and then you have the final amount of carbon-12. So the whole time we're analyzing carbon-12, which means that we don't need to convert really into moles to have a comparative relationship or anything like that. We're always comparing same atom with same atom. How much of that same atom is left? T is your measurement of time, and tau is your measurement of half-life. You can replace this by lambda if you feel uncomfortable doing that. There's textbooks that have both symbols for this equation. All right, and as long as your t and your tau are in the same units, that's all that matters. Yeah. NO is the initial amount. So, oh, I didn't write a different definition. Amount of material. Yeah, that's a mistake. Amount of material at time t. And N naught is the starting material, the initial amount. Yeah, because some things are measured in years and something are measured in milliseconds. All right, so let's do a real quick example. How much time is required for copper 66 that has a half-life of 5.120 minutes to decay 99.9% of its mass? You guys prefer the lights on or lights off? Off? On? On? Yin Yang, what did you say? On? I prefer on. Those of you who might be a little bit rusty with your algebra, if I had this equation here, how would I solve for t? What would be the first thing that you would do? You would do what? The log? Be more specific. What do you mean? Exactly. I have to do the log of both sides, right? So it'd be the log of 0.999 would be equal to, if it's a log rule, you can bring down the exponent. Did I do something wrong? You're right. Yeah, you're absolutely right. This should be what? 001. Yeah, that's right. Sorry about that. That's right, huh? Because it's 999. So 0.01 would be 99%. 99.9% is 001. its percent, is 0.1 divided by 100. So log of both sides would be the log of 2 multiplied by negative t over 5.20 minutes. Then you can solve for t. Since I decayed a lot of this, and I'm never going to actually decay 100% of my material, do you expect this to be a short amount of time or a long amount of time compared to the half-life? Long, right? Many half-lives had to occur for me to decay this much of it. So I'm looking at a number. If I did this correctly, I'm thinking of a number that's way bigger than 5.120. Someone have an answer? 51.0. So 10 half-life. Is that correct? Everyone's in agreement. Okay. So yeah, so you can say that 51.0 minutes have elapsed since in order for me to decay 99.9% of this material. You could also refer to this as the number of half-lives that have passed, right? So you can do 51.0 minutes divided by 5.120 minutes, and this gives us approximately 10, and that's basically telling us that 10 half-life cycles have happened for me to have 99.9 of the initial material to be decayed. Am I ever going to have 100% decay? No. So we can use this to date things, and actually this is the last topic. We're almost done, actually. I didn't think it would be this fast. So radioactive decay can be used to date things. And you guys have heard about, how like we prove that, fossils are a certain age and things like that. One caveat is that it's been proven to be not the most accurate. So there are better ways of doing it now. Now they use something called uranium dating, but carbon dating is still quite valid. I mean, a lot of like anti-science people will say it's garbage. It's not garbage, though I do admit it's not the best science. The reason for that is because it can only be used to measure the age of things that used to be living at some point. Right? And I'll explain why that is. So it relies on this idea that there are isotopes that are less stable than more stable isotopes. And so, okay, let's take a look at it, see what's happening. So first thing we need to understand is that there are these things called cosmic rays that enter our atmosphere. And our atmosphere is made up of what? Mostly? Nitrogen. Nitrogen is the most abundant molecule or even atom in our atmosphere. It composes of 71% of the mass, and that's the majority, right? And what happens is when the cosmic rays enter the atmosphere, this is a kind of irradiation, a kind of energetic waves that's coming from the sun that's exciting the nitrogen molecules and turning them into carbon 14. Okay, and so what's going to happen is you have your nitrogen, which is 714, plus something is going to give you carbon 14. So what kind of radiation did it give you? Did it give the nitrogen? It gave a minus or yeah, beta plus radiation. So the sun gave a beta plus radiation, and converted this nitrogen into a less stable carbon isotope. So the nitrogen is stable, but because of the energy received from the sun, it becomes this unstable carbon 14 isotope. And this has a half-life of about 5,730 years. Yep. And the thing is, it doesn't stay that way because it's not stable, right? It's going to decay, and it's going to decay um, back to nitrogen 14, all right, over time. And we can figure out if we knew the starting amount of carbon 14, we can figure out based on how much is left, we can figure out how old. But why this thing had to be living is the following. So you have this now carbon 14 in the atmosphere. Carbon takes the shape of which molecule in the atmosphere? CO2, exactly, right. So CO2 is where the C in the CO2, some minor percentage of it is going to be C14. All right, most of it's going to be C12, but there's going to be some parts of it that are going to be C14. And everyone is exposed to this isotope of carbon because this happens everywhere in the atmosphere. Now, what's interesting is that there are plants who do something special with carbon dioxide. What do they do? Yeah, what is photosynthesis? Exactly, exactly, right. So they convert the carbon from carbon dioxide into carbon from glucose, and glucose is C6H12O2. It's matter now, and animals consume it, plants consume it, animals consume it, microorganisms consume it. Essentially, because of plants, they're fixing this carbon 14 isotope, and every organism is eating it, right? And then once you die, unfortunately, it's dark, once you die, do you breathe anymore? Do you eat anymore? No. So what happens when you die is that your intake of carbon 14 stops, right? So while we're living, we have a steady intake of carbon 14. So a living organism has a predictable amount of carbon 14 inside because they breathe in, they eat a fixed amount of this. I mean, it's averaged out over a very long time, but we eat and we breathe a fixed amount of this. Um, So we breathe CO2, we eat the glucose, and we incorporate that C14 into us. But once we die, we stop eating, we stop breathing. So no more new C14 enters us. So now we can figure out the average living organism has what percentage of C14? And then you have a specimen of a dead organism, and you can see, okay, well, this organism has a percentage of that C14 remaining because it decayed back into nitrogen 14, right? So based on the ratio of those two, you can figure out what's the remaining amount of carbon 14, and then you use that with the half-life to determine how old that object is. So here it is. So you have the carbon cycle, which is the CO2 cycle that the plant fixes into glucose and animals breathe. And then we have to do the actual mathematical equation. So the equation is as follows. This is an equation that I'll give you. NF and over NO is the final amount of carbon 14 divided by the initial amount of carbon 14. And we know the initial amount because all organisms breathe in a certain percentage of what's available in the atmosphere or what's available in the plant. We often look at NF over NO as just a ratio. Right? Again, if you're uncomfortable with this H, you can write lambda, you can write tau, whatever works. I wish I made an example of this. Okay, how old is something that has 60% of its carbon-14 left over? 60. How old is a fossil with 60% of its half-life remaining? Sorry, 60% of its carbon-14 remaining. So that requires us to know what the half-life of carbon-14 is. I'm just going to remind you. It's 5,730 years. Oh, sorry. Based on what I given here, do you expect it to be less than or more than one half-life? More than one half-life? Less? The answer is more? Did I make a mistake somewhere? Should be less. What did you get as an answer? That doesn't make sense. Let's look at this. Why is that the case? What am I doing wrong here? I think there's something wrong with my equation. Okay, so I'm going to guess that there's something wrong with my equation. I'll look it up and then I'll email you guys if I find the actual answer. But if I don't find it, then I just won't put on the exam. There you go. Yeah. I have a feeling there's something wrong with my equation because 60% is less than half of it's being decayed, right? So why would it be more than one half? I'll have to look that up. Okay. 0.6. What did you put 0.6 in the equation? Or did you put 60? Yeah. Oh, the denominator? It's supposed to be 0.6? Could be. Okay, so what's you're saying is 0.693. So that would give us an answer of 4,000 years? That would make more sense. Okay, let me just look up real quick. You finally looked it up? Ah, okay. All right. Thank you, Linda. It was very observative of you. Okay, so let's change this equation to 0.69. So that would give us an answer of 4,223. See, it's always good to look at the answer and say, well, that doesn't make sense because it should be less than 1/2 life. And that made us find a mistake that we made, or that I made. All right, so any questions on this? Moving on to the last one slide. So I just wanted to mention a bit about nuclear fusion and nuclear fission. I told you guys about this at the beginning of class. It was just that you have to follow these laws when you're talking about any kind of nuclear reaction. So you have to conserve the charge, you have to conserve the nucleons, and you have to conserve the mass energy. And I have just an example here real quick. So using the conservation criteria, determine the unknown element F. It seems very daunting at first, but it's actually very, very straightforward. You basically just have to add up the nucleons to make sure that they make sense. While you answer this, what kind of decay is this? Alpha decay, exactly. How did you know that? Yeah, because you produce the helium atom. So here I had 1 proton, here I had 3 protons. Therefore here on this side of the equation I'm supposed to also have 4 protons. And 2 of them are being used by the helium atom. So that means my X has 2 protons. And I have 1 neutron here. Sorry, not 1 neutron, but 1 nucleon. And 0 neutrons. And this is 6 neutrons. So I'm going to get how many nucleons in my unknown? How many? Yeah, 4. So just real quick, I have 1 here. I'm going to go back to protons. I have 1 here and 3 here on this side of the equation. I should have the same number of protons on that side. So 2 of them are being used by this helium atom. And so if there's 4 and I've already used 2, that means this one's going to have 2. And again, here I have 1 and 7 nucleons. That have 8 nucleons. And I've used up 4 of them here. That means I have 4 remaining, so that's also going to have 4. I wrote this in terms of neutrons, but that might be confusing, so forget about it. So my X atom is going to have 4 up here. I'm just going to erase what I wrote here. So what has 2 protons and 4 nucleons? Helium, yeah, exactly. So this is just another helium atom. So the final equation is 1 hydrogen plus 7, 1 hydrogen with 1 lithium is going to give you 2 times helium of this energy. Any questions? Anyone recognize this? What's that from? From Fallout, yeah. More game stuff. All right, so that's basically it. Waves, optics, and modern physics. The office is open. My office is open for sure. Now, whenever my office is open, as long as I'm in school, you guys can come in, drop by, and see if you have any questions. You can ask them to me. On Monday, for you guys in the afternoon, I have questions. I don't have questions. I'm answering questions. If you have any, if there are problems, if there are things that was maybe confusing, you guys can come and ask them, and I'll do them all on the board. No problem. Yeah. Okay. I see what you mean. I have to see if I have any. But if I don't have any, I'll write at least 1 or 2 myself so that you can practice. But that's can't do more than that. They'll just keep that. Aside from that, yes, so you can, for further questions and all that stuff, come and see me, come and see Lee if you want to hear it a different way, because I don't pretend to have the best explanation for things all the time, and it's always better to hear it from someone else sometimes. I try to explain it to yourselves, ask yourselves how it works. And take that, I mean, I keep preaching that to you guys, that you should keep talking and conversing. I still am, right? Especially next year when you guys are going to be doing harder things. Always, teamwork is always better. And then I know that our sport makes it so that, that you want everyone else to do bad so you can look better. Put that aside, it's always better to learn in groups than it is to learn alone, right? So try to find yourselves a group of people to study with. The stuff that you're going to learn in university are going to make this stuff look like kindergarten school stuff. Just like you thought the high school stuff was kindergarten school stuff. It's always the last thing you do is always easier than the current thing. And it's never going to get easier. So it's always better to find outlets to make it easier for yourself. It was an honor to teach you guys, right? Some of you for just one semester, but most of you guys for 2 semesters. I had a lot of fun in my first year as a teacher. I think I started off being a little bit too high schooly, and then I overcompensated by being way too hard. And then I think I figured it out for this course. So I don't know, maybe you guys, maybe you did. Um, in any case, it was a pleasure. Hope you have good luck in your finals and good luck next year. Hopefully, I see some of you at the correspondence. If I don't see you for the exams, if I don't see you there, then good luck for right? See you guys. Oh, I have the photo.